Hello, welcome back. We're doing Chapter 7, Section 1, Exponential Functions, Growth and Decay. We have two more videos with two more examples. An example of exponential growth and an example of exponential decay. In the previous examples, the application problems, we talked about values. We talked about how much a guitar increased in value because it's rare and valuable, and how much a truck depreciated or decreased in value because that's how buying cars work, buying automobiles work. This is an example of the world famous doubling example, and this is coming from biology. So we'll talk about this in class, but this is where we have a life form, in this case it's a bacteria, that reproduces by asexual reproduction. Okay, so basically one bacteria splits into two bacteria, and we end up doubling over and over again. So what we're going to do is we're going to write the function that represents this. We're going to graph the function, which I've already graphed it on Desmos, and I'll show you what that looks like. And then we'll try to use the graph to predict how many bacteria are alive, part of this, after 12 hours. So before I'm going to change that, okay? This is the function for growth that we had, and we used it for money. It works in this case too, okay? So we have the amount at time t. That's the amount, the number of bacteria at time t. And notice this doubles every hour. If you watch the previous videos, I said it that way. If you watch the previous videos, I mentioned that financial problems usually have an interest rate per year. But that's not always going to be the case, and for problems that are not financial, like this biology problem, the doubling, it's nice. It's doubling every hour. I don't know if the bacteria know, hey, it's an hour, we better make more bacteria. Interesting that they predicted it that way. Okay, not every life form does that, okay? All right, anyway, so this is going to be the amount that I have at the beginning. I started with 150. And it's going to increase by 100%. So this is going to be 1 plus 100%, which, spoiler alert, is 1 to the power of t, which is every hour. Okay, I can simplify that and say 100 times 2 to the power of t. And if I think about this, let's say if I just take one bacteria, okay? So at 0 hours, I get 1 bacteria. After 1 hour, it doubled, now I've got 2. After 2 hours, it doubled, and I've got 4. Here's my 1, 2, 4 again. 3, 8, 4, 16, 5, 32, etc. That's if I started with 1 bacteria, but I didn't. I started with 150. So I have to take all of these and multiply it by 150. So that would be 150, 300. Now I've got 600, 1200 or 1200, 2400. So I don't know much about this particular type of bacteria, but I know that people usually have bacteria in their mouth. And if you ever watch those Listerine commercials when they say it washes all the bacteria away, there's always a couple that are left. They start reproducing, and if you don't brush your teeth pretty soon, the number of bacteria in your mouth is going to explode. Of course, I don't know if that's what this bacteria is. You should talk to that over with your biology teacher. So this is the function that represents this, and I'll rewrite it. Okay, so for part A, I get the number of bacteria, the amount, is equal to 150 times 2 to the t power, or if you want to say 1 plus 1, that's fine. Okay, part B, we need to graph it. One more time, you can graph it like this. If you do, you're going to have to play with the window to match it up with what you see, or you probably are going to be able to do Desmos, and I don't have my other iPad here, so I'm not going to show you the Desmos, but this is what it looks like. Now check this out. I have exponential growth. There's a couple of cool things about this, okay? First of all, this does not exist. because you can't have negative time. Okay, so it has to actually start at 0. T equals 0, and you have 150 bacteria. And if I look at that, that looks like it's really close to 0. That's because to draw this in Desmos, to draw it so where you can see this, I had to shrink my y-axis really far down. I had to zoom really far out. My question, part C, is predict the number of bacteria after 12 hours. Well, I already kind of know what that is. That's why I had to draw it this way. Okay? And it's kind of hard to see what these are. Okay, what the actual values are. Notice that it's really, really low, but after 5 hours, it starts to curve up. And then it curves up. And remember, what's happening is it's doubling. It's doubling. So like this distance right here doubles and I get that distance. And then I double it and I get that distance. So it keeps doubling and doubling and doubling and doubling. Again, this is exponential growth. The population is blowing up. Okay? The question says, use the graph to predict the number of bacteria after 12 hours. Okay? And we're going to interpret that as the number of bacteria at 12 hours. And of course, it'll be more than that after. So here's 5, 6, 7, 8, 9, 10, 11, 12. This is 12. So I'm going to follow my line up, and it's going to be about, well, it's kind of hard to tell, about right here. Maybe, maybe not. And if I go over to the side, so for my part C, this is my part B, this is my graph. For my part C, it's going to be over, because it's kind of hard to tell, 600,000, because that's a little bit over that. And if I was doing this with Desmos electronically, I would do x equals 12, I'd make a vertical line, and I'd find out where the intersection is, which is how that works. So, if you got nothing else out of this, just remember, make sure you brush your teeth 2 or 3 times a day.